Hello and welcome to today's video. In this episode, we're going to dive deep into one of the most fascinating and mysterious concepts in modern physics, the wormhole. Wormholes have captured our imagination through countless science fiction stories, movies, and TV shows.
There, that's it. That's the wormhole.
You say it, don't spread it, wrong.
The idea of stepping through a tunnel in space-time and ending up in a distant region of the universe, or perhaps even another universe entirely, is both thrilling and bewildering. But just how realistic is this notion? Are wormholes genuine astrophysical objects that might one day be used for interstellar travel? Or are they merely speculative solutions to complex equations with no tangible counterpart in the real world? We'll explore the theoretical foundations of wormholes, how they emerge from Einstein's field equations, and the challenges involved in actually creating or maintaining one. We'll also discuss whether wormholes could serve as portals not just across vast cosmic distances, but potentially between entirely separate universes. Most importantly, we'll address the question: could humans, or any form of matter, actually travel through a wormhole safely? So, buckle up and join me on this journey through space-time as we seek to uncover the truth about wormholes. Foundations of wormholes. To begin, let's define what a wormhole actually is. In the simplest terms, a wormhole can be envisioned as a shortcut through the fabric of space-time. Imagine a two-dimensional sheet of paper representing our universe. Normally, if you want to get from one point on the paper to another, you'd travel along the surface. But if you fold the paper in just the right way, bringing two distant points close together, you could potentially poke a hole straight through. This hypothetical hole connecting one region to another is the wormhole. The concept emerged from solutions to Einstein's equations of general relativity. Einstein's theory shows that mass and energy can curve space-time. Under extreme conditions, the geometry of the cosmos might allow for shortcuts, bridges that, in theory, connect different regions or times. These were first discussed seriously in the context of the Schwarzschild solution and what are now known as Einstein-Rosen bridges, named after Albert Einstein and his collaborator Nathan Rosen. It's important to note that while wormholes can exist mathematically, mathematics alone doesn't guarantee their physical existence. The jump from theoretical possibility to actual astrophysical object is immense. Einstein-Rosen bridges. Einstein-Rosen bridges were the earliest theoretical wormholes to be studied. In 1935, Einstein and Rosen published a paper describing what seemed to be a bridge-like solution of the gravitational field equations. Initially, these were thought of as connections between different parts of our universe. Later, physicists realized these solutions were actually describing black holes and their mysterious innards. A classic Einstein-Rosen bridge is essentially a non-traversable wormhole. That means if you imagine a black hole connected to a white hole, the hypothetical time-reversed counterpart that spews out matter, you'd have something resembling a wormhole. But there's a big catch. Such a structure would only exist momentarily and then collapse, and any attempt to travel through it would be thwarted by intense gravitational forces. Moreover, there is no evidence that white holes exist at all. As intriguing as these wormholes might be on paper, they're not the stable, usable tunnels we see in science fiction. In modern theoretical physics, the term wormhole is often used to refer to hypothetical structures that could be stabilized, at least in principle. But to keep them from collapsing, you'd need what's known as exotic matter, a form of matter with negative energy density, something we have never observed in nature. Theoretical underpinnings. The mathematics of general relativity allows for solutions that resemble wormholes. However, just because the equations permit a certain shape of spacetime does not mean nature chooses to realize it. Physicists must ask, are wormholes stable solutions, or are they mere mathematical curiosities? Stability is a crucial issue. Without exotic matter to hold the wormhole's throat open, the internal passage would collapse faster than anything could traverse it. Additionally, quantum effects come into play. Quantum field theory suggests that fluctuations of energy in the vacuum of space tend to destroy any would-be wormhole, shutting it down before it can be used. Another theoretical consideration involves the famous energy conditions. These are certain inequalities that matter and energy must obey. Classical matter that we know of respects these conditions, meaning no negative energy densities that would allow wormholes to remain open. If exotic matter is required, then physicists must explain where it comes from and how to harness it. Despite these hurdles, some researchers remain intrigued. Studies in string theory and quantum gravity attempt to reconcile wormholes with more fundamental frameworks. Perhaps in a future theory of everything, wormholes might emerge as natural phenomena under specific conditions. Until then, their status remains uncertain. Quantum mechanics and exotic matter. Let's talk more about exotic matter. Why is it so crucial? Wormholes require what's called a negative energy density inside the throat. Negative energy might sound like science fiction, but quantum mechanics does allow for certain kinds of energy fluctuations that in principle could produce something akin to negative energy. The Casimir effect, for example, shows that placing two conducting plates very close together can create a region of space with a lower vacuum energy than elsewhere. This is often cited as a hint that maybe, just maybe, some form of exotic matter could exist. But here's the problem. The amounts of negative energy produced by known quantum effects are minuscule. To hold open a macroscopic wormhole, you'd need a tremendous amount of negative energy. It's unclear how to scale up such effects to astronomical levels. Without a clear mechanism, it remains strictly hypothetical. Furthermore, even if we did manage to create or find exotic matter, we'd then face the engineering challenge of shaping and maintaining a wormhole. The energies and pressures involved are currently beyond our wildest technological dreams. As of now, we are nowhere near producing stable wormholes, but that doesn't mean future breakthroughs are impossible. Practical challenges and hypothetical uses. If wormholes could exist and be stabilized, what could we do with them? The science fiction scenario is to use them as cosmic shortcuts, enabling interstellar or even intergalactic travel in reasonable time. Instead of spending thousands of years crossing the cosmos, you could step through a wormhole and emerge light years away almost instantaneously. Another tantalizing possibility is using wormholes to connect not just distant locations in space, but different epochs in time. Under certain conditions, a wormhole might allow for a kind of time travel, raising all sorts of paradoxical scenarios. Could you send messages to the past? Could you visit future civilizations and bring their knowledge back? Yet, before we get carried away, let's remember that none of this is currently feasible. The technical and theoretical barriers are enormous. Wormholes, if they exist, might be so tiny that only subatomic particles could pass through them. They might also appear and vanish spontaneously, leaving no stable structure to exploit. Moreover, even if a stable, human-sized wormhole could exist, the gravitational and radiation conditions near its throat might be lethal. Wormholes in popular culture and science fiction. It's no surprise that wormholes are a staple of science fiction. From Star Trek to Interstellar, writers and filmmakers have used wormholes as plot devices to enable rapid travel and communication across vast distances. Such stories spark our imagination and inspire real scientists to explore what's possible. They also serve as educational tools, introducing complex scientific concepts to general audiences in a captivating way. However, the depiction of wormholes in fiction often glosses over the enormous theoretical and practical difficulties. Movies might show a spaceship casually entering a wormhole and emerging safely elsewhere, but real physics suggests that the tidal forces, radiation, and instability would pose immense dangers. Still, science fiction can motivate us to learn more and to keep pushing the boundaries of our understanding. So, could wormholes really be portals to other worlds? The honest answer is, we don't know for sure, but it seems unlikely with our current understanding of physics. Theoretical models allow for their existence under exotic conditions, but we have no direct evidence that wormholes form naturally in our universe. Even if they do, making them stable and traversable appears to require forms of matter and energy that we have yet to discover. For now, wormholes remain a fascinating theoretical concept, one that challenges our understanding of spacetime, relativity, and quantum theory. They serve as a bridge between known science and the uncharted territories of what might be possible. While we may never walk through a wormhole to visit another galaxy or timeline, the quest to understand them pushes physics forward, compelling us to ask deeper questions about the nature of reality. Thank you for joining me on this journey today. If you found this discussion interesting, consider subscribing, and let's keep exploring the mysteries of the universe together. Until next time, stay curious and keep looking up.